Motion is everywhere. It's the changing position of an object. When something moves, it changes its place in space. We see motion in flying birds, running cheetahs, and even the Earth revolving around the sun. There are different ways things can move. Linear motion is movement in a straight line, like a car on a highway. Circular motion is movement in a circle, like a spinning top. And then there's oscillatory motion, a back and forth movement, like a pendulum swinging. Understanding motion is crucial to understanding the universe. From the smallest atoms to the largest galaxies, everything is in a constant state of motion. It's the foundation of physics and many other scientific disciplines. To delve deeper into the fascinating world of motion, let's explore the groundbreaking work of Sir Isaac Newton. His laws of motion revolutionized our understanding of how objects move and interact. Sir Isaac Newton, a brilliant physicist, gave us 3 fundamental laws of motion. These laws explain how objects behave when forces act upon them. The first law states that an object at rest stays at rest, and an object in motion stays in motion at the same speed and in the same direction, unless acted upon by an unbalanced force. The second law tells us that the force acting on an object is equal to its mass times its acceleration. This means that heavier objects require more force to move or stop than lighter objects. Think about pushing a shopping cart versus pushing a car. The car requires much more force due to its larger mass. Finally, the third law states that for every action, there is an equal and opposite reaction. When you jump on a trampoline, you exert a downward force, and the trampoline exerts an equal upward force, propelling you into the air. Newton's laws are fundamental to our understanding of motion. They explain why things move the way they do and allow us to predict how objects will behave under different forces. Inertia is the tendency of an object to resist changes in its state of motion. This means that an object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more massive an object is, the greater its inertia. Imagine trying to push a heavy box across the floor. It takes a lot of force to get it moving because of its inertia. Once it's moving, it's also difficult to stop because it wants to keep moving in the same direction. Inertia plays a crucial role in our daily lives. It's why we wear seatbelts in cars. Our bodies want to continue moving forward even when the car suddenly stops. It's also why it's important to warm up before exercising. Our muscles need time to overcome their inertia and prepare for movement. Friction is a force that opposes motion between 2 surfaces in contact. It's the reason why objects slow down and eventually come to a stop. While it might seem like a nuisance, friction is essential for many everyday activities. Think about walking. Without friction between our shoes and the ground, we wouldn't be able to move forward. Friction also allows cars to grip the road and turn corners safely. However, friction can also be detrimental. It causes wear and tear on moving parts in machines and generates heat, which can be wasteful. There are different types of friction, including static friction, kinetic friction, and rolling friction. Static friction prevents objects from moving when at rest, while kinetic friction acts on moving objects. Rolling friction, as the name suggests, occurs when an object rolls over a surface. For a more comprehensive understanding of motion, its types, and the forces that govern it, visit http://www.skillscoach.co.in. It's a valuable resource for delving deeper into the fascinating world of physics and beyond.
From the smallest atom to the largest galaxy, the universe is in a constant state of motion. It's a mesmerizing dance of objects, each following its own path across the cosmos. Understanding the laws that govern this motion allows us to comprehend the very fabric of our universe. It's a journey that takes us from the everyday occurrences, like a ball soaring through the air, to the awe-inspiring movements of celestial bodies. In this exploration, we'll embark on a captivating journey into the world of motion. We will unravel the fundamental concepts that shape our understanding of how objects move and interact. Get ready to explore the principles that govern the movements of objects big and small, near and far. Our adventure begins with the basics, the language we use to describe motion. From there, we'll delve into the intriguing difference between uniform and non-uniform motion, unraveling the mysteries behind their distinct characteristics. Fasten your seatbelts as we prepare for an exhilarating ride through the fascinating world of motion. To truly grasp the intricacies of motion, we need to familiarize ourselves with its fundamental building blocks. These essential concepts form the foundation upon which our understanding of motion rests. Imagine you're watching a runner sprint down a track. How do we describe their movement accurately? Firstly, we have displacement, which refers to the overall change in an object's position. It's about the journey from a starting point to an ending point, regardless of the path taken. Think of it as drawing a straight line from where the runner began to where they finished. Next comes speed, a measure of how quickly an object is moving. It tells us how much distance an object covers over a certain period of time. In our runner example, speed would tell us how fast they are running in meters per second or kilometers per hour. However, to fully capture the essence of motion, we need velocity. It combines speed with direction, giving us a more complete picture of an object's movement. If our runner is moving at 10 meters per second towards the finish line, their velocity is 10 meters per second in the direction of the finish line. Finally, we have acceleration, which measures how quickly an object's velocity changes. It occurs when an object speeds up, slows down, or changes direction. Our runner accelerates when they burst off the starting line, and again when they make a turn on the track. Now that we've grasped the basic concepts, let's explore the two fundamental types of motion: uniform and non-uniform motion. Imagine a car cruising down a straight highway at a constant speed. This is a classic example of uniform motion. In uniform motion, an object covers equal distances in equal intervals of time. Its velocity remains constant, without any changes in speed or direction. This serene and predictable motion is often found in controlled environments or idealized scenarios. However, the real world is rarely so straightforward. In most cases, motion is non-uniform. Here, an object's velocity changes over time, either in magnitude or direction, or both. Think of a car navigating a bustling city, accelerating, braking, and turning as it maneuvers through traffic. Non-uniform motion is characterized by varying speeds and directions. It's the motion we encounter most often in our daily lives, from a leaf fluttering in the wind to a roller coaster twisting and turning through the air. To delve deeper into the realm of motion, particularly uniformly accelerated motion, physicists have developed three powerful equations. These equations provide us with a mathematical framework to analyze and predict the motion of objects. The first equation, v equals u plus at, connects final velocity v to initial velocity u, acceleration a, and time t. It tells us that the final velocity of an object is equal to its initial velocity plus the product of acceleration and time. The second equation, s equals ut plus half at squared, relates displacement, s, to initial velocity, u, time, t, and acceleration, a. This equation allows us to calculate the distance covered by an object undergoing uniform acceleration. Finally, the third equation, v squared equals u squared plus 2as, links final velocity, v, to initial velocity, u, acceleration, a, and displacement, s. This equation is particularly useful when we don't have information about time. These three equations, working in harmony, provide a comprehensive toolkit for understanding and predicting motion under constant acceleration. They are essential tools for physicists, engineers, and anyone studying the intricacies of movement. Section 5. Momentum, the power within. Moving beyond the basics of motion, we encounter the concept of momentum, a measure of an object's resistance to change in motion. It's a fundamental property that depends on both an object's mass and velocity. Imagine a bowling ball and a tennis ball rolling towards you at the same speed. Which one would be harder to stop? The bowling ball, of course, due to its greater mass. Momentum, denoted by the symbol P, is calculated using the formula where m represents mass and v represents velocity. Momentum plays a crucial role in understanding collisions and interactions between objects. In a closed system, the total momentum before a collision is always equal to the total momentum after the collision. This principle, known as the law of conservation of momentum, is a fundamental law of physics. Section 6. Newton's second law of motion, momentum in action. Sir Isaac Newton, a towering figure in the history of science, formulated 3 laws of motion that revolutionized our understanding of the physical world. His second law of motion provides a profound connection between force, mass, and acceleration. Newton's second law states that the net force acting on an object is directly proportional to its mass and acceleration. This means that a greater force will result in a greater acceleration for a given mass. Mathematically, this law is expressed as where F represents force, M represents mass, and A represents acceleration. This equation can also be written as where dP represents the change in momentum and dt represents the change in time. This form of the equation highlights the relationship between force and the rate of change of momentum.